We'll take a look here at constructing and analyzing of graphs. Get an intro into this idea. So before we get started there, let's talk about some of the variables. There's two types of variables you guys can interact with, and one's a categorical variable. And really, it's exactly what it sounds like. You're breaking things up into categories. So, for example, eye color, favorite food, favorite color, versus quantitative, where these things take on quantities, or there's a range of numeric values. Here, height, weight, income levels. Within quantitative, you could have a discrete quantitative variable, so something that has a finite possible number of values, countable. An example, number of goals in a soccer game. You could have 1 goal, 2 goals, 3 goals. Versus continuous, where there's an infinite number of values. So the height of males at Cardinal Gibbons. So you think about this, a little bit different take on it. You could be 62 inches, 62.1, 62.3, 62.35, versus in soccer, you can't score 2.35 goals or 4.87 goals. It's countable. So discrete is kind of a countable 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 example, versus continuous, you can keep breaking it down into decimals and smaller fractions, pretty much continuously, if you will. So there's an infinite possible values. So a couple of quick examples. So gender. Gender would be something you break into categories. Telephone area code. Despite the fact that there are numbers involved, area codes are used to categorize where people live. So think about 919. That tells you that somebody lives around the Wake County area. The amount of electricity that you use at your house. Well, that is an example of a quantity. And beyond that, you could use a continuous amount of electricity. You could use 26 megawatt, 26.1, 26.13. So you can break it into decimals. So not only is it quantitative, we can go a step further and say it's continuous quantitative. Zip code, similar to area code, even though there's numbers, your zip code breaks you into a category where your mail comes. So that's categorical. Ticket sales at Darius Rucker concert. Well, that's a quantity. And this would be a discrete quantitative because you can sell 1 ticket, 2, 3, 4, 5, 6, but there's no way to sell 7.82 tickets. So that's a discrete quantitative value. The number of chicken eggs that'll hatch on November 17, 2013 at 3 o'clock in the morning. Well, that's quantitative again, and it's discrete. It's countable. You can't have 6.28 chickens hatch. Now, a really, really good way to go back and filter, is it quantitative versus is it categorical, is if it makes sense to take the average. So go back and look. It takes, to take the average for average ticket sales for Darius Rucker, that makes sense. The average amount of electricity used, that makes sense. To find the average zip code or the average area code for telephone numbers, there's no point in doing that. I guess you could because they're numbers, but it's not data that can be used versus the average number of chicken eggs that are hatching. Like that's something that somebody that is interested in those chickens, perhaps the farmer or whatnot, is interested in. So when you're talking about categorical data, 2 main types of graphs. You can have a bar graph. Notice the bars don't touch. And right away you see as well that these things are broken into categories down here. Right? We've got categories. The drugs, the violence, the corpses melting, naughty words being used. And then we also kind of break it down of those reactions. Another type of categorical data graph would be a pie graph. And here, very, very useful for comparing parts to a whole. So, 20% of people say this, 10%, 14%, 16%. Just make sure that at the end of the day, when you do these, that you end up, all of your percentages add up to 100%. Now, so percentages work really, really well for pie charts versus the bar graphs like you saw earlier. Those are really, really good for counts. Like 20 people said this, 10 people said this, people said this. So quantitative variables, you can have a dot plot. And we've actually used dot plots in the class already. Really, really useful for small sets of data where we put, I think we used X's with the jelly blubbers, right? So that's an example of a dot plot where, if this was 17, 18, 19, we'd put dots or X's where the observations were. A stem and leaf plot, also really, really good for small sets of data. And you get a little bit more information. So the way a stem and leaf plot works, we'll get into more detail down the road, but it's a good tool for small sets of data. And in my opinion, you get more information than a dot plot because you actually use the values, the quantitative values to build the graph. So you're using the numbers 17 and 18 and 19 to build a graph. The box and whisker plot. A lot of you guys have probably seen these before, where it looks like there's a box and then a couple like cat whiskers, and there's lines that pop up along the way. But typically what you use these for are larger sets of data. And the disadvantage of a box and whisker plot is suddenly you lose some of the data points. You no longer see the individual data points versus you kind of start to see an overall shape of the data set or where data appears, but you only have access to a few specific data values. And again, we'll get into more detail as we progress through the unit. A histogram is probably something a lot of us are very, very familiar with. They're very useful for larger sets of data, and you can end up, quote unquote, losing some individual data points because all of a sudden, unlike the box plot that you saw on the previous page, a histogram, a lot of times the x-axis, you'll start to get, 17, and then you'll get 20, you get 23, and then all of a sudden, instead of individual data points, you get bars that represent the height, how many things are in each particular bin. You lose the individual data points in lieu of a quicker way to kind of group everything together. Okay, there's 20 observations here, 22 observations there, and then we'll just draw a quick bar. An ogive, which is going to be probably a new graph to pretty much everybody, and it's a type of graph that's going to show percentiles, or another way to think about this, you're going to get a sense of a relative standing. A lot of times, you're not necessarily going to have to graph these, but we want to be able to be familiar enough to read them. And it's a unique type of graph that allows us to see this, especially helpful if we no longer have a normal distribution, because normal distributions, we have access to things like normal CDF and the inverse norm. If it's a non-normal distribution, we need another way to talk about percentiles, and that's how an ogive can actually help us out. Just as a warning, graphs can be misleading. Here's a graph that was actually published. Notice this thing was published by AOL in March of 2006 on the number of deaths in Iraq. And all of a sudden, it looks like the number of deaths had gone down quite a bit. But if you look back at the title, you see all of a sudden this is in March. That's only a quarter of the way through the year, so we'd expect the deaths to be a lot lower. But somebody used this data to try to tell a story at some point along the way. People can use these graphs to tell their own version of a story or make what seemed unconnected connect. All of a sudden, here's this graph about stopping global warming, but probably none of us would think that we could get some type of relationship between global warming and the number of pirates in the world. So apparently, as the number of pirates has decreased, the global temperature has increased. So obviously, according to this graph, we need more pirates in the world to stop global warming. So again, graphs can be used to show seemingly unconnected things, and people do this all the time in the real world. As they're presenting data, they can connect two things that have no business being connected to try to tell their story. As you guys start to create some of these graphs, let's remember there are three things that will always occur on every graph you make. You want to make sure they have a title, you have an axis that is labeled, an X and a Y axis, and you want to make sure that you're identifying any units that you use. As we're being asked to describe the data, describe the distribution, analyze the distribution. There's a lot of ways we can see this question asked, but it's basically asking for four main things. We're going to talk about the shape, and we'll talk about what these look like in just a second, but some of the adjectives you can use: mound, symmetrical. Things can be skewed. They can be single peaked, multiple peaks, bimodal, unimodal, uniform, and we'll look at some examples in just a minute. We want to talk about outliers. Is there an observation that just doesn't look like it belongs with the rest of the data? Like, that's something important to pass along. It could be an indication of data that's been incorrectly recorded. It might just be a strange observation that we should keep an eye on down the road. We want to talk about the center, the middle of the data, and the two most common are the mean and the median. You also want to talk about spread. So a big one that you guys all know about already is the range, but you might also talk about standard deviation, which we talked about last unit. Standard deviation, especially in a statistics setting, standard deviation is something that a lot of people pay attention to. It makes a lot of sense once you kind of use it for a while. Sometimes you might include outliers, sometimes you might take them out. It kind of depends upon what you're interested in telling. So going back to shape, just this idea of mound-shaped and symmetric. So here's some examples. A lot of times what I like to do is go through and just kind of draw a curve over the top. And you can see there's the mound shape. It doesn't really look like it tails off in either direction too poorly. So not exactly symmetric. So we might even throw the word in here, relatively symmetric. All right. So if it's not symmetric, it might be skewed. And if something is skewed left, it seems sort of counterintuitive. If I draw that picture, you can see it tails off to the left. So the skew direction follows the tail. So in a skewed left distribution, most of the data is actually to the right. It's the few data points off to the left, kind of all by themselves, that is quote unquote skewing the data. So for something to be skewed right, you can see that it kind of tails off to the right. Most of the data, the high peak of the data, is to the left, and it tails off as you go down. So the tail, follow the tail for skew. Something that's bimodal, you can see has kind of two distinct peaks. Another way to think about this, the mode is the most occurring data point. Well, there's kind of two things that appear a lot. Two, meaning bi, right? It's kind of like saying there are two modes, or two things that happen the most. That's another way of thinking about bimodal. Something that's uniform, they're pretty much straight across. There might be a little bit of variation, which we would expect, but in general, it's pretty much straight across. As you're using SOCs, sometimes it's not appropriate. You think about this primetime TV censorship, it wouldn't be appropriate to use SOCs here. Because one, how would you get a measure of center? Somewhere in here between graphic, gore, and corpses melting, how do you do that average? And how would you get a range here from drugs to nudity? There's no way to get an actual range. The other thing, these bars, I can move naughty words over here, and all of a sudden what seems to look like it's skewed to the left, I can move the bars around. There's nothing keeping those bars in those places. So the big thing to realize is actually SOCs is not appropriate for these bar graphs and pie charts. In other words, it's not appropriate for categorical data. And if you go back to the very beginning, talk about can you take the average as a great way to tell if it's quantitative? Well, average is one of those measures of center. So if you can't take the average, it's probably categorical, which means you cannot use SOCs.